All right, welcome to the Explainer. Today, we're going to tackle something huge, RSA encryption. It's this incredible algorithm that, kind of behind the scenes, became the foundation of trust for our entire digital world.
So let's start with a puzzle. How do you share a secret in public? I know, it sounds like a riddle, doesn't it? But for centuries, this was one of the biggest, thorniest problems in all of cryptography. Think about it. If you want to send a secret message, you need a secret key to lock it up, and your friend needs the same key to unlock it. But how do you get that key to them safely? If you just send it, someone could grab it on the way. And cracking that puzzle, well, that's how you understand why RSA was such a game changer.
Yeah, this whole thing has a name, of course. It's called the key distribution problem, and honestly, before RSA showed up, it had the world of secure communication just stuck. I mean, completely bogged down in this frustrating, endless loop.
Okay, so let's break this down. The old way, what we call symmetric keys, was basically like having a single physical key for a lockbox. Super simple, right? But here's the catch. If I want to send you a locked box, I also have to get you the key. How do I do that without someone making a copy? For something like the internet, it's just not going to work. And this is where RSA's asymmetric system completely rewrote the rules. Instead of one key, you get two. There's a public key, which you can think of as an open padlock. You can hand these padlocks out to everyone. And then there's your private key, the only key that can open those padlocks, and you keep that totally secret. So anyone can snap your padlock on a message, but only you can open it. Genius, right?
So, how did they do it? How did the inventors, Ron Rivest, Shamir, and Leonard Adleman, which is where we get the name RSA, how did they finally crack this code back in 1977? Well, the answer wasn't in some fancy new computer chip or complex piece of hardware. Nope, it was in the pure, beautiful, and kind of mind-bending mathematics of prime numbers. And here's the thing. The basic idea is surprisingly simple. You start by picking two absolutely massive prime numbers, and you keep them secret. Then you just multiply them together. A computer can do that in a blink of an eye, creating one gigantic public number. But here's the magic. If all you have is that giant final number, trying to figure out which two primes you started with, well, that's basically impossible. For a regular computer today, we're talking it could take literally centuries. It's a mathematical one-way street. And that is the entire foundation of RSA's security. This whole concept has a really cool name. It's called a trapdoor function. Think about it. It's super easy to go one way, multiplying the primes, but it's computationally insane to try and go backwards, unless you have a secret. That secret, knowing the original prime numbers, is the trapdoor. It's the secret shortcut that lets you, and only you, reverse the process and decrypt the message. It's just so elegant, and it's the absolute heart of why RSA is so strong.
And look, this wasn't just some clever idea stuck in an academic paper. No way. This breakthrough almost immediately jumped from the page to the real world, becoming the foundational technology for building trust across the entire internet.
I mean, seriously, its impact is woven into pretty much everything we do online. You know that little padlock you see in your browser when you're shopping on Amazon? That's HTTPS or TLS, and it's using RSA to make sure your credit card number is safe. Or think about a Windows update from Microsoft. How do you know it's legit? They use an RSA digital signature to prove the code is really from them and hasn't been messed with. It's even in things like secure email, remote access, and even some of those two-factor authentication tokens, like the classic secure ID fobs. It's everywhere. But it's not a perfect fairy tale. For all its mathematical brilliance, the story of how RSA has been used in the real world, it's got some pretty dramatic twists and turns. See, its security doesn't just rely on the math being solid. It depends entirely on how people use it. And what's so fascinating when you look at these major incidents is that the attackers never actually broke the RSA math. Not once. They were way more clever. They went after the systems around it. Back in 2011, with a secure ID breach, hackers didn't do complex math. They just used phishing to trick people into giving up secret data. In 2017, the RSA vulnerability happened because a computer chip was flawed and created weak, predictable prime numbers. And just recently, in 2023, the Marvin attack brought a 25-year-old flaw back to life, exploiting how servers responded to errors. It's the perfect reminder, right? A chain is only as strong as its weakest link. So, for decades, RSA has been the king. It's reigned supreme. But now there's something new on the horizon, a new kind of computer that doesn't just look for weak links. No, This threat aims to shatter the entire mathematical foundation that RSA is built on.
4,099. That's the number. That's what keeps cryptographers up at night. Right now, today's quantum computers are not there yet, not even close. But a stable machine with just over 4,000 logical qubits, it could do something that takes our best supercomputers centuries to even attempt. It could find those secret prime numbers in a matter of hours. And just like that, our gold standard of encryption would be completely, totally useless.
So how does it do it? Well, there's this thing called Shor's algorithm. And you have to understand, a quantum computer running this isn't just a faster version of your laptop. It's not guessing keys faster. It's using the weird, wonderful rules of quantum mechanics to go straight to the heart of the problem and solve it directly. To put it another way, it doesn't bother picking the lock, it just walks right through the door. Because the door itself was never designed to stop something that can be in multiple places at once.
And this is why it's such an urgent problem right now. There's this strategy called harvest now, decrypt later. It means adversaries are scooping up and storing all of our encrypted data today. They can't read it yet, but they're betting that in 5, maybe 10 years, they'll have a quantum computer that can unlock all of it. This is a ticking time bomb for any secret that needs to stay secret for a long time. We're talking government intelligence, corporate trade secrets, even your private health records.
Okay, so it sounds a little bit like doom and gloom, right? But the story doesn't end with a quantum apocalypse, because while one group of brilliant scientists has been building these revolutionary new computers, another group has been just as busy building new kinds of shields. A whole new generation of cryptography is already here, ready to protect us. And the solution is this whole new field called post-quantum cryptography. One of the new standards is an algorithm called Kyber, and here's the key. It doesn't use prime numbers at all. Its security is based on a totally different kind of math, based on something called hard lattice problems. The best way to think about it is, imagine trying to find your way through an incredibly complex, multidimensional crystal maze. It's a problem that we believe is just as tough for a quantum computer to solve as it is for a regular one. The only real trade-off? The keys are a little bit bigger, but what you get in return is a future-proof lock.
And this isn't just theory. The transition away from RSA is already happening. You've got the big tech giants already experimenting with these new algorithms, and governments are starting to set some serious deadlines. But let's be real. Upgrading the entire planet's digital infrastructure is, well, it's a monumental task. This is the next great cryptographic migration, and whether we succeed or not is going to define digital security for the next generation. So the biggest question on everyone's mind is, can we get it done in time?